Proteus is a true interdisciplinary research program that brings together unique and world-leading engineering, optical physics and chemistry. The program is driven by clinical need and clinical pull and has a real focus on disease diagnostics. In particular, we are interested and focused on lung diseases, and this includes diseases such as lung cancer, COPD and acute respiratory distress syndrome. But more broadly, the Proteus technology can be used in any disease area and any organ system. Proteus has synergistically combined the various tools and technologies that have been developed across the research program and across the research team to build, design and construct the Kronoscan imaging system. This is a next generation imaging system that has unique capability in the optical imaging of disease. The Kronoscan imaging system in essence consists of three main components. The first of these is produced by the engineering team in Edinburgh. This is a CMOS SPAD detector, which is one of the fastest and most sensitive detectors on the planet. The second component is produced by the University of Bath and is an imaging fibre. This is made from telecommunications glass and allows us to produce the world's first disposable imaging fibre. The third element of the Kronoscan system is a suite of chemical reagents or chemical probes produced by the chemistry team in Edinburgh. This allows us to paint at a molecular level disease in patients. These three elements are combined together to give the full Kronoscan imaging system. In this system, the imaging fibre is passed down the working channel of a bronchoscope deep into the lungs of a patient. There we can deposit small amounts of the chemical reagents that will light up disease. This allows us to then diagnose disease in patients in real time.
What we've developed is an optical fibre-based endoscope which has several thousands of individual light channels in it, which each one acts as a pixel. And these pixels butt up against tissue and transmit information from the distal lung to a system outside which can record the image. In addition to this imaging fibre, our first endoscopic tool also incorporates two fluid channels for delivery and extraction of fluid from the distal lung. So this could be a smart probe to help visualise bacteria, for instance, or take a sample for analysis externally in a lab. When we develop optical fibres, obviously the first thing you think of is the telecommunications industry. What we've done is use the same materials and equipment which has been developed for the telecommunications industry in order to create low-cost, bespoke optical fibres for use in medicine.
So yeah, the sensor is a very beautiful little device. It's got a 512 pixels. It's actually a line sensor. So it's not a conventional sort of rectangular camera sensor, but you can build a camera around it. The reason it's a line sensor is because we split the light into its constituent wavelengths. That's a crucial thing. And this line sensor can essentially give us 512 separate wavelengths of light in parallel. The other aspect that's quite exciting is that the pixels on the sensor can detect single photons. So it's extremely sensitive. You can capture single photon events. In addition, we can put timestamps on each of these photons. So every photon that comes along gets a timestamp, and that enables us to build a picture, a detailed picture of the photon arrival time.
Okay, so if we take a step back and think about what traditional fluorescence imaging is, this is where you shine light onto your sample in one colour, the sample absorbs that and then sends it back to you in a different colour. That's a very powerful technique and give you lots of information, for example, the structure of tissue. So if you go into the lung, you can see the alveolar spaces, you can see the bronchi and things like this, and you can see how bright the light that came back was, but that's about it. The extra dimensions that we are adding is in Kronoscan is, for instance, the lifetime imaging. Here, we don't just look at the brightness of the light that comes back, we time the process. So when we shine the light in, we start our stop clock. We wait, when the light comes back out again, we stop our stop clock. And that's a process called fluorescence lifetime. Now that process is not just dependent on what the molecule is, it's dependent on where the molecule finds itself, its environment. And it's going to be very useful for looking at different tissue types. So for example, cancerous tissue and healthy tissue, while they look quite similar in terms of color and sometimes really quite similar in structure, their lifetime is different. So we can use that lifetime information to distinguish between the two. On top of this, we developed a suite of smart probes. These are probes that are also fluorescent, but importantly, There's a green-on-green issue when you try and look at probes that fluoresce at the same colour as the lung tissue. So lots of probes, for historical reasons, have emitted in the green. The lung tissue also emits in the green. So you have an issue there of distinguishing the two. But if your probe has a longer lifetime, let's say it holds onto that light a little bit longer than the lung tissue does, then we can use the lifetime process to distinguish between the lung tissue and that probe. Furthermore, Kronoscan can look across the colour spectrum, so we can look at probes that are green, red, orange, all at the same time, and so we can multiplex together a whole multitude of different signals to get the maximum possible information out from in the lung.
The interface is used by different types of user. So clinicians are the main target, but we also have biologists, engineers and so on who are interested in this data. It's very important for the clinician in particular that we keep the interface as simple as possible. So the interface is built as a desktop application. It's written in Java, and it basically interfaces with the sensor through a very fast USB 3 interface.
Fibre-based techniques are compatible with existing diagnostic approaches, such as bronchoscopy. Current technologies such as optical endomicroscopy use a thin fibre which delivers light to the deepest areas of lung tissue and allows clinicians to visualise lung tissue in great detail through the autofluorescence of elastin. Optical endomicroscopy allows us to identify areas of abnormal lung tissue, however it does not distinguish benign from malignant disease. Currently, we have to use CT scans and tissue biopsies to do this. Kronoscan allows us to evaluate lung tissue in much more detail. As a real-time imaging diagnostic instrument, we are able to distinguish bacterial infection from lung inflammation, reducing uncertainty and allowing us to deliver antibiotic therapy quickly, improving the likelihood of a successful outcome for the patient.
So in summary, the EPSRC has supported a visionary research program. It has led to fundamental research, but most importantly, its application in the clinical space. The Proteus program has the real ambition to commercialise the Kronoscan imaging system and technologies, such that it will enable and support decision-making by clinicians.